Hello and welcome back to Broadcast Focus. My name is Russell Trafford-Jones, and today we're looking at how the move to software, and usually this involves the cloud, has changed media transport. We'll be exploring why it's hard to get to live media into the cloud and why SRT isn't always the answer. On Broadcast Focus, we talk to the people behind the industry, and so talking about his part in developing this new technology, I'm delighted to introduce Andy Rayner from the VSF.
Greetings.
Hi Andy, how are you doing?
Oh, good, thank you. Yep.
Thanks for joining me, and we spoke at actually the IBC Kickstarter Day for the upcoming accelerator this year, which I'm looking forward to. And we just started talking really about the fact that we've got this new technology coming along, and I think more and more people are going to be interested in it. And so I wanted to really dig a little bit deeper. Now, you're the director of the Video Services Forum, a director, and what's the aim there? And this is where all of this technology is coming from.
Yeah, so the Video Services Forum has been going for quite a long time. It's a US-centric media industry organized, professional media industry organization. I think I'm the only board member outside of the USA, but it's been going for a long time. It was designed, if I recollect, to actually bring end users of media services together with vendors in a way to actually build out standardized ways of doing stuff in the industry and making things work end to end. So I've been involved significantly for the last, I guess, 12 years or so. And yes, been a director for a fair bit of that, and been excited to be part of quite a few of the initiatives that VSF has been doing. I mean, for those of you that are not familiar, some of the key achievements VSF has done: standardization of the interfacing of JPEG 2000. There were two different versions of that released in 2013 and 2018, if I recall. Also, the precursor, or effectively the development of what became 2110, was a series of a couple of technical recommendations that were developed by VSF. So again, the groundwork, the tech groundwork, was developed within VSF that then became that SMPTE standard as it was evolved. So some key initiatives, and I think the initiative we're going to be talking about today is another one of those VSF ones called GCCG.
Trips off the tongue.
Yes, yeah. You have to say that very carefully to get it out right.
So the idea of GCCG is that we're trying to move video primarily, but obviously we've got all of the other types of essences, and it could be into the cloud, but it could be otherwise, couldn't it? Somehow video needs to be moved around, and I think a while ago, was it over 10 years? I'm not sure. We developed SRT as a now a de facto standard, I guess. And we're not talking specifically about that type of protocol, which would really just trying to talk about how to get video from A to B. So what's kind of the difference in aims of the GCCG and something like SRT or nowadays RIST?
Yeah, so SRT and RIST are both ARQ technologies. They're specifically technologies that sit around typically an RTP UDP stream that's streaming media from one place to another, and they are basically a tool to guarantee integrity by retransmitting lost data. That's what both SRT and RIST do. They obviously have other bells and whistles associated with them. Both of them have the ability to encrypt data as part of it, and RIST has been developed with quite a few extra features since the original basic ARQ retransmission request element, to have things like GRE tunneling, so you can tunnel together different feeds, etc. So those two technologies were developed as an integrity tool. The GCCG work was designed for two to accommodate two main things, really. So first of all, there is a trend in the industry for more and more live production media processing to be done in compute in various forms. And we need to, some of that compute may well be locally on appliances, servers in your own infrastructure, but increasingly that's either in a data center somewhere else, or it's in public cloud. And this picture that you've put up here is what uses the term I call distributed production. But basically, this is a kind of a catch-all diagram. To give credit to this, this was a diagram or a set of diagrams that the DPP produced about 4 years ago now, which basically articulate examples of the different ways that production is now being done. And if we look at that top one, the traditional on location, that was your original studio way of doing a production, where your acquisition devices, all of your processing and storage, and all of the controls thereof were co-located within a studio and a gallery. And when you did an OB, you similarly took all of that stuff with you. So you had a truck on site and all the cameras connect into the truck, and you do all the storage and processing and control within the truck. And what we're seeing now, specifically really enabled by IP connectivity in the wide area and the local area facilitating this, is actually these different models of the way production's done. And that actually has sustainability advantages, because you actually need to ship a lot less stuff. And it also means just much more flexibility and cost saving in the workflows to do these different ways of control. And what we're saying is fundamentally these diagrams are showing you're disassociating the acquisition physical location from the processing location from the control place. And that bottom one there is showing you specifically cloud. And I guess by when we say cloud, quite often we mean public cloud. But the other models there, like the centralized one, etc., the more and more we're moving to compute to actually serve those processes, whether they're hosted privately or publicly.
Yeah, so it's about moving data en masse, effectively, and
I guess getting back to the diagram you had, the cloud, the ground to cloud, cloud to cloud, cloud to ground, that specifically what we are trying to address within this working group within Video Services Forum is to say what we want is a standardized way of getting data into cloud. Be that private or public. We want a standardized way, and I need to expand on this because this is the if you like the core of it, of getting data between compute, within compute, getting the media data flows, and then getting them back down to ground, if you like. And so there's two very fundamentally different approaches there. In the world that we're in, typically the ground to cloud bit is a streaming interface still, and will be for quite a long time, I think. So that's when your SRT that you were talking about, or any ARQ technology such as RIST, plays in. Also, there are other technologies such as SMPTE 2022-7, which is a dual path RTP layer redundant healing process. And there's also the potential of FEC. So all of those technologies can be used to actually provide the integrity or guarantee the integrity of the transit from the linear streaming transit in and out of cloud. The challenge we've got, and there's various people who've been talking about this in the industry for quite a while now, is once we get into compute, compute doesn't natively lend itself in its bare format to actually doing linear streams that are perfectly perfectly spread out. So this diagram you've got up now, as part of the SMPTE 2110 suite, which is a suite of basically largely initially uncompressed video, audio, and other essences individually being carried to carry these media flows. We spent quite a lot of time honing this 2110-21, which is what's called the timing piece, and that was designed to actually specify the linearity of the data flows that you need to have. And the reason we need those linear data flows is to avoid packet loss, because if you have lots of bursty data, as is natively produced by a computer, if you don't constrain it by a software output, if you actually aggregate lots of highly non-linear streams together and you're carrying them UDP, not TCP, so you've not got the handshaking mechanisms, then there is a high risk of losing data. And in the early work in 2022-6, which was the linear compressed format for IP before we got to 2110, there was observations in various places that without a timing profile, you actually risk losing data. So what we're coming to here is 2110, and being someone that was significantly involved in helping to make that come about, I'm very passionate about it. But once we get into compute, 2110 really is not the ideal tool, because it's UDP based and because it needs high linearity. So what we've been saying is, in the industry, we really want an interoperable way of handing data between compute instances that's compute friendly. So it doesn't have to be conformant to very stringent timing requirements, because it doesn't need to, as long as we have integrity. So the key things in that compute to compute thing that requirement we're looking for, there are two fundamental requirements. We need the integrity of data transfer, and we need it to be done in a timely manner. It needs to be time bound in some way. Now, different software platforms, be they publicly hosted or private, have got different underlying architectures of providing those transports. Now, on a fundamental level, obviously, computer data is normally transferred via TCP, but there are other ways of doing that, and different cloud providers have got different underlying technologies. But what we've been trying to do in this VSF GCCG work for that cloud to cloud bit, the compute to compute bit, is abstract ourselves, saying we're not worried about, we'll make an assumption that the integrity layer, the integral and time-bound layer exists. And what we want to do is provide an API that actually allows you to hand the data off between compute instances, that doesn't have to have all of those time linear requirements that we traditionally have been, I guess, requiring for the last 90 years of broadcast, as we've gone from everything from the original, analog video signals right the way through to up to and including 2110. So it's a new way of looking at the way we hand data on. The one other thing that goes alongside that is, as soon as you break that linearity of stream, the timing information associated with each piece of media data, each clump of media data, becomes more critical. Because if you run a hose pipe process, which is how I would consider any of these linear streaming protocols that we've been using since whenever, those inherently, you can work the timing out just because one packet follows another, and if you just line them up and linearize them, you get the stream. Once we actually move into a compute environment, then that is by essence, excuse the pun there, by its very nature, a non-linear processing machine, and that's fine. That's what it needs to do, and that's how compute works. So, but we do need timing information associated with each clump of media that's being handed off, to allow us to make sure that we faithfully reconstruct the right things and merge the right things, etc., at the right times in terms of the processing we do.
So to just to recap some of that, then the part of the problem, if I'm correct, of having having streams which are not linearly produced is that when you're funneling 20 or 100 of them through the same port on a switch, then sometimes that's going to get congested because they've burst up to, and then sometimes it won't be very congested. So ideally, if everything's really well paced, then you can calculate how much a port can handle. But if you're not doing this 2110-21, then what you're saying is that the switches can get overwhelmed.
Yeah, and in a UDP world, that means packets get lost.
Yeah,
obviously RIST and other technologies, ARQ technologies, effectively are UDP based, and they ask for retransmits because the packets have got lost. But that you then have a latency hit because obviously you've got the recurring request loop, etc. Having said that, some of the underlying technologies that the big providers like AWS use under the skin to provide the integrity of data transfer is effectively UDP with ARQ happening on a micro level with small fragments of data that they're transmitting and hashing in different places. So the fundamental technologies are similar. It's just the way they're being used and actually enables that.
And I think it's probably worth noting that I think a lot of people's experience, or at least what even if it's not their experience, what you think of when you're trying to send something, imagine trying to send something into the cloud, you just think of an encoder, and an encoder produces effectively one stream, because if you assume it's an MPEG transcoder or encoder or JPEG 2000 even, you're getting basically a stream out and it's going into the cloud, and it doesn't seem that difficult. Is one of the main benefits, apart from the timing that we can talk about in a second, is one of the main benefits of this GCCG that for things like 2110, we're bundling all of these separate essences up into that same into this same tunnel and the same path.
So there are actually some flexibility there. I mean, one of the things we've tried to achieve on that ground to cloud bit is creating effectively some operating points. So we recognize that there's different profiles of level of kind of available bandwidth and quality and latency that's required. So we've defined at a high layer like JPEG XS, which is which is a relatively low compression ratio, so it's relatively high bitrate flows, but actually very low latency. The actual compression decompression is sub-millisecond in terms of the what's needed, the time needed to compress and decompress. But also we've defined operating points for 422 10-bit HEVC/AVC, and then sort of the lower profile 8-bit 420 type stuff where you're actually doing lower quality but still very adequate for many applications. So those profiles, so we've tried to define those profiles and the protection mechanisms in that streaming format as well. And those can be essence based or composite based. So obviously if it's a TS, typically be that an AVC or an HEVC or even an XS TS, as in TR07, then that's effectively composite. The video and audio are together. But the original definition we did, the very first one we ticked off was TR08, which is essence based using 2110 flows coming in, but with the 2110-22 compressed essence. So typically that's another very effective way of doing JPEG XS transport. And there are a couple of different models we've got for that. The whole concept, which I think is worth reminding ourselves, one of the original drivers of 2110 was to keep the audio and video and other data as separate flows, because you don't want to, push a whole load of video into an audio processing facility, and you don't need to push all of the audio into the video stuff. And typically, in a production workflow, the audio does need a different path of different functions on different routes to the video, etc. And in the cloud, the same's true, regardless of whether we're processing on compute or in hardware. The same principles are true. So I do like the essence-based transfer because that has that flexibility. But at the same time, the other challenge it gives you then is the fact that you've got the relative timing of the different flows that you've got to somehow maintain. And that's probably a whole nother talk for us to do at another point on some of the work that we're doing elsewhere.
Yeah. And so, and I guess it's some of those current drivers. I was at that I wanted to cover now, at the IBM State of the Industry at event at NAB. They were talking about cloud adoption. I think that was where it was, and that that's obviously still high on the agenda, but mainly for larger organizations, as in the larger the organization, the more sure you would be that they are probably in production in the cloud and certainly working on doing more and more. And that's fair, and that's kind of what we see in the day to day. And so I think for anyone who's not directly working with one of those broadcasters, it's probably worth appreciating, and tell me if you think this is correct, that the aspirations of working in the cloud is to do is to go as close as possible to what you're doing in a studio, particularly if it's production. And so those drivers to produce in the cloud is not simply to get stuff in the cloud and do the production. It's also to be as professional as possible. And traditionally, we've said professional means high quality, low latency. And so it feels to me like the GCCG work is built to enable something which hasn't quite really come to fruition. People are still trying really hard, and some people are succeeding, don't get me wrong, but to put into the cloud these high quality streams, whether it's JPEG XS or even 2110, where that's possible, is that part of is this an enabler to that, or is that just by the by?
So in some ways it's an enabler. There are, of course, other technologies which are having wide adoption that are becoming de facto industry standards, like NDI, which is taking a lot of cloud use. Interestingly, NDI is an interesting case because it's a streaming interface, a streaming protocol. You're pushing, it's that hose pipe, you're pushing the data out. Two of the key observations about native NDI as first introduced, one is it's a highly VBR thing, so it's variable bit rate, so it's entropy based transport. The other thing is it defaults to TCP, so actually it provides you in a compute world that kind of guaranteed integrity just by the fact it uses TCP rather than UDP, which in a compute world actually has some pluses. Obviously, there are quite a lot of other challenges that NDI has in terms of the scalability, and again, there's another whole topic there, but potentially picture quality as well, which I know is being gradually evolving. But so there are reasons why people choose different technologies, and I think the cloud enabler is an interesting one because it's really kind of it's democratizing content production, because actually you can get very cost-effective tools and very cost-effective ways of doing production, which mean that actually content producers have a cost-viable way of doing live production on things that would never be used, on events that would never be able to be afford to be covered before.
Yep.
And I think the other thing about event-based usage for production is, you've got broadcasters that are doing 24/7 channels where quite possibly on-prem compute is actually a more cost-effective route for them. But if you're looking at doing events-based production where it's 2 or 3 or 4 hours 2 or 3 times a week, then that kind of the architecture of cloud-based production and those kind of things really hits an efficiency perspective, because you're calling on the compute when you need it, and then you can let it go, and it doesn't cost you anything for all the majority of the time of the week when you're not using it.
So talking about this standardization of interface, with this, are we trying to I guess there's two questions here. We'll come to timing in a moment as a technology and the way it works. But you mentioned the ability to add a time to everything. So obviously with 2110, it has its own timestamps. I don't know if they're relevant by the time you get into another environment. Let's say you're moving them between private clouds. But is there an element here where is this simply a description of how to bundle and streams together and get them from A to B, or is there also an API style element to help with the to help interface with the compute?
Yes, so timing is absolutely critical, and obviously you want to preserve the information about the relative timing of the feeds that you're getting in, because that's important. Because if you've got, for instance, in a future application, I can see, the truly like pop-up production could be a number of 5G enabled cameras, for instance, and a few 5G enabled microphones that you rock up at an event. You plug your half a dozen cameras in and pull out your microphones, and all of them separately send those feeds, over wireless infrastructure back to a cloud production center or cloud processing. And you actually need to obviously co-time like the different cameras that are being used, and even more critically, if you're trying to do phase coherent audio images, you need to co-time your audio feeds as well. So the timing is really, really important, and part of what we're trying to do in the GCCG work in the C2C bit is to actually define the way that timing can be transferred from potentially a 2110 Essence timestamp, but there are other ways of getting timing in if you're coming in over TS, or maybe you actually just say, okay, as I ingest those flows, as they hit my software ecosystem, I actually want to give them initially timestamps, which I can then create offsets if I can see they're needed as part of the workflow to normalize that. Again, another topic for another day would be the work that we're doing separately in 2110-11 in SMPTE on timing through the whole production chain, because that's a whole point. That's a whole nother challenge. But specifically in GCCG, we're focusing on the timing information, the propagation of that timing information as you go through the different compute processes.
Okay, and so obviously as part of 2110, you would expect there to be timestamps, but the GCCG is built for many codecs, and some of which don't have the timestamp. So there's that extra ability to add timing information and stamp them as it goes through.
Yeah, absolutely. And one of the deficiencies of 2110, which we're trying to work on at the moment with this -11 work, is the fact that timing that origination timing information, by the nature of the way 2110 has been implemented by most people in the industry, you lose it at the next hop. So once you propagate downstream, you don't actually have any knowledge of the relative timing that's been implied on the different or incurred in the different flows.
And then similar to that, then is there an attempt, or is GCCG intended to actually carry a PTP signal to allow you to synchronize them, or is that just a different task for a different technology?
So one of my big pushes, contentions here, is precision time is really not needed in compute. And there was a lot of work done, or a lot of concern in the early days of talking about taking live production into compute, where everyone's saying, well, we can't do it because we can't have PTP. Now, there are absolutely points in the chain where you need precision timing. So when you're reconstructing a linear stream, then you need to have a very precise time to do that. Also, ideally, all of your origination devices need to have a common accurate time, so those timestamps are common across all of those devices. again, audio is probably the most critical there, because if you actually want to create a phase coherent audio image from different acquisition points, you need sub 20 microsecond timing accuracy as a minimum to actually be able to reconcile them. So high precision timing information for the origination point is really, really important. But as long as you have those timestamps associated with the clumps of data, until you reconstitute at the far end of your compute chain to get to when you go back to what I call a linear stream, you don't need precision time. And actually, for most of the processing that's going to happen, in those compute workflows, something akin to NTP level of granularity of accuracy is going to be absolutely sufficient for what's needed within the compute workflow.
Yeah, that makes sense. And of course, the audio industry was an adopter of PTP a long time ago, a long time before we started thinking about 2110. So
the audio AS67 was the foundation and the precursor to the 2110 suite. And as you know, the audio element of 2110 is basically a subset of the AS67 spec. So we learned from the audio people that did it first. Yeah.
Cool. All right. Well, look, let's bring this to a close. I think it's been really good to look at that and really just understand the what GCCG is trying to do, and perhaps just before we close up, where is the project in terms of the progress, because clearly there's supposed to be drafts and then it's published, and are there any implementations? Just give us a flavor for where we are in that process.
Yeah, so we're at an exciting place. So a few weeks ago, I think it was the end of February, effectively, we published a draft of the GCCG work, which is available on GitHub. That slide that we had up earlier, which showed the ground to cloud and cloud to cloud bit, that has the GitHub reference on it, but you can look at it up. Oh, there it comes. Yes, the GCCG-API. So we published effectively the work we've done on GitHub, and we're inviting comments. And as we record this on the 23rd of April, that is still a very valid that's open. So that draft is there. My dev team in Appear, as an example, have actually been working hard at looking at implementing this, and have also posted quite a few comments against the draft as it currently stands, which is being worked through by the team. So I would encourage anybody else in the industry that's wanting to look at this, go in, pick up the stuff from GitHub, work through it, and we would really appreciate further comments. I think we said post NAB we were going to start looking and trying to address this. So I'm expecting that possibly next week or moving onwards from then, we're actually going to be starting to try and take these comments on board and move from a draft, hopefully, to a first release of this, I guess probably within the next month or so. So a very pertinent time for us to be talking and to invite comments.
That's great. We heard it here. Strike while the iron's hot. Go over to GitHub and have a look at that. That's really good. Thanks for that, Andy. And talking about striking while the iron's hot, make sure you subscribe to the channel, because that'll be really helpful. And it will bring a smile to Andy's face as he sees the numbers climb. So thank you for that. Really appreciate your time with us, Andy. So thanks, and I look forward to speaking to you again in the future.
Thanks, Russell. Take care.